showing global ocean circulation, shown at about 3 days per second for about, this is just under a year, this is 9 or 10 months of data. We actually have this analysis for over 20 years now, from 92 to present. And we're actually, right now, working on a higher resolution version of this with an oceanographer upstairs. It's in my office as we speak.
That's amazing.
So this is a big calculation. This is this is a petabyte scale calculation. So here's the Gulf Stream shedding these mesoscale eddies. And in general, you see that the flow field is dominated by these kind of curled up, narrow current streams. So this is the famous mesoscale eddy field. This is a 9 billion pixel image looking toward the center of our galaxy. So these are all stars. They've probably all got planets. This image is about the size of your little fingernail at arm's length, with a lot of stars. And there's a lot more stars than these, but they're all behind these stars.
So, and you know, and it's things like this that let Pete say, there's got to be another Earth somewhere. It's unbelievable that there's not another one like us somewhere.
Right, so there's a big sample. Okay, so if this doesn't make you feel small enough, let me show you one last.
Yep.
So here's about a chunk of the universe about 1 billion light years across. We're starting from a couple 100,000 years after the Big Bang with a uniform distribution of matter. So this is dark matter, because most matter is dark matter. And now we're evolving this to the present. So the simulation spans about 13.5 billion years. And you can see the development of this kind of web-like structure. X that you see here, our galaxy. So that's the big picture. This agrees very well with observational data. This is just an n-body simulation, which is about 440 terabytes of data, by the way. Okay. So this is a big calculation. Many billions of points representing the dark matter. Okay, so we can obviously put big movies across multiple screens, which is useful when there's a lot of resolution. And as Rubak says, this is an order billion grid point, several billion grid point scale, unsteady computational fluid dynamics simulation, showing the flow associated with V22 rotor system without the V22. This also illustrates
all the vortices off the tip, right?
Right. So the features we're seeing are vortices. We're identifying those through the Q criterion, if you're familiar with that, and then we're mapping onto the vortices another scalar quantity, in this case the magnitude of vorticity, and this basically gives us an idea of the strength of the vortex. Basically these purple guys are the strongest, they're the blade tip vortices. They give rise to all sorts of secondary vortices. The qualitative feature of the flow that the CFD guys have learned from this, basically you get this kind of spiral of blade tip vortices that washes down. The blades themselves actually push down this helical sheet, and we're seeing a slice of that in these blue lakes. This helical sheet actually gets blown down faster than the enclosing vortices. So there's this kind of shear from the center on the outside, and that produces all these secondary green worm-like vortices.
And you can see that because if you look right here, you can see that this vortex and the sheet start off at the same time, but this thing is accelerating down faster,
right,
causing these worms.
We have over 120 gigabytes a second of connectivity with upstairs down to the rendering cluster that's driving this. So we can kind of split the calculation, offload the post-processing feature detection and so forth, retain essentially a compressed version of the data set in the form of feature detection, so we can re-render this from different viewpoints. We can kind of fly through this and so forth. But we don't have to store the entire three-dimensional unsteady vector field, which is a lot larger.